Good evening. Well, you might be watching this in the morning, so for you, good morning. Anyway, hey, this is Coach Seckinger, science teacher, Midland Middle School, and I'm back here again, but we're not talking about magnetism tonight. We're talking about electricity. There are no rules when you're watching this YouTube video. The only purpose is to help you prepare for a vocabulary test. What I suggest is that you pull out a sheet of paper. On the next slide, you're going to have a list of all the terms. You pause this video, you write down all these terms, and as I talk about the definition, see if you can recognize the term that we are talking about. If you don't want to do that, that's fine. You can just simply watch the video. I would argue that just watching the video would be enough to kind of help you prepare for this test. Remember that before there was YouTube, there was actual studying. So don't let this video replace just reading the book and going through the chapter, using your flashcards, and so forth. With all that being said, I want to thank you for coming back. I think this is a great way to prepare for this test. It says a lot about you as a student that you're going to take your time in your evening to do this. I hope you get a lot out of this. If you will, after you watch it, please feel free to leave a comment. Those of you who want to get extra credit, you need to leave a comment. And hey, if you got anything you can say that can make this better and do better next time, then let me know. But again, this is Coach Seckinger. I want to thank you for being here, and let's go ahead and get started. Okay, these are our terms. They begin with electric force, and we're going to end with Ohm's law. Remember, you don't have to, but I think that you should write all these terms down and see how well you do as we go through each and every one of these definitions. Bam! Our first definition: the attraction or repulsion between electric charges. If you said electric force, you are correct. If you were watching me in class using the Van de Graaff generator, that metal ball, you realize that when I got close to it, sometimes I got popped in the head. In fact, one time I got popped in the eye. Didn't feel good. Well, that all relates to this second definition. The second definition is that region around a charged object where the object's electric force, that push or pull, that attraction, that repulsion, is exerted on another charged object. Again, this area where you have this attraction or repulsion, this region, well, we call that the electric field. If you got it right, good job. If you didn't, well, hey, just stick in there. As we've talked about electricity, you know that electricity can flow. It can flow like a river, or it can collect. You can walk on the floor and you can rub your feet on the carpet. This definition applies to electricity that collects on an object. It builds up on an object, and it does not flow continuously. Again, if you've ever touched the knob of a door or a car handle to get in a car, or you even touch someone and you've gotten shocked, well, you've gotten shocked because of a buildup of a static electricity on them or on that object. Again, this term, static electricity. Remember that one. This is a key term in this chapter. Hey, we're moving on. We have mentioned this vocabulary word several times this year. This word, this time, we are referring to the transfer of electrons from one uncharged object to another by rubbing, by that direct contact of rubbing back and forth. And I just rub my hands back and forth, and I don't know how that's going to sound. But again, the transfer of electrons from one uncharged object to another by rubbing. Good luck. Well, if you mention friction, well, then you're correct. Again, friction is one of those words that we've used it several times this year in several different contexts. When it comes to electricity, when we say friction, we mean the transfer of electrons through this rubbing action. Good job. The previous vocabulary word that we talked about was friction. And friction was the contact, the direct contact between an uncharged object and another uncharged object. Before those two objects rubbed together, neither one had a charge. However, this next vocabulary term, it refers to direct contact, but before there was contact, each object both had a charge. So the formal definition is the transfer of electrons from a charged object to another object by direct contact. Again, do not get this confused with friction. Okay, if you said conduction, you are right. Do not get conduction confused with friction. Friction is the rubbing, the direct contact between an uncharged object and another uncharged object. Conduction is a transfer of electrons from a charged object to another object. Good job. Okay, in this next definition, we're still talking about having one object give a charge to another object. However, when we talked about friction and conduction, we talked about direct contact. Friction was contact between an uncharged object and an uncharged object. Conduction was direct contact between a charged object and an object. However, if you have a charge, you can still give an object another charge, whether that's a positive charge or a negative charge, without touching. So the formal definition is the movement of electrons to one part of an object that is caused by the electric field of a second object. And remember, the electric field extends out from an object. So if the electric field can have an impact on some other object without there being any actual touching. So good luck on this one. This one's a hard one. If you chose induction, awesome. Hey, I mentioned friction and conduction, so some of y'all just used the process of elimination and said, hey, the only one he hadn't talked about yet is induction, so it must be that one. But again, remember, induction involves no direct contact. If you remember when I was using the Van de Graaff generator in class, as I was getting my hand near it, the hairs of my hand were sticking up and they were pointing straight to the Van de Graaff, which was telling me that the Van de Graaff generator, this electric field was having an impact on the charge of the hair on my arm without there being any direct contact. So good job on this one. It's a hard one. Oh, how nice it is sometimes to touch something and to get a spark. Sometimes this spark is bright enough to where you can actually see it. It heats the air around the path until the air glows, and you can see this line of electricity going from one object to the next. Okay, again, the formal definition is the loss of a static electricity as electric charges transfer from one object to another. Okay, remember, static electricity, it builds on an object. It doesn't flow, it gets there, and it stays. And if it comes into contact with something that has an opposite charge, well, there's going to be attraction there, and it's going to move from one to the other. That movement can sometimes generate heat where you can see it. Sometimes it can generate some pain. Good luck with this one. Okay, again, this is the loss of static electricity as electric charges go from one object to another. We call that static discharge. Good job. We have spent most of this time talking about electricity that's sitting on an object. It got there through rubbing or conduction or induction, and it's not really doing anything. It's just sitting there and it's waiting for you or whatever that object is to come into contact and for the electrons to kind of jump ship and go somewhere else. Now let's talk about electron or electric charges that are flowing. It's just continuous movement like a river. The formal definition for this next term is the continuous flow of electric charges through a material. Again, we're talking about something that's flowing, that's moving. The word is electric current. If you can, in your brain, if you can try to compare the flowing movement of electrons like the water in a river. We call water moving in a river, we call that a current. Well, when we say that electricity or the flow of electrons is moving in or through an object, we say there's an electric current. Good job. This word has come up a lot, and we're going to talk about it some more in the class. The formal definition is an unbroken, complete path through which electric charges can flow. I've used the NASCAR track as an analogy, a highway that goes in the circle. Again, the complete, unbroken path through which electric charges can flow. If you said electric circuit, you are correct. Again, imagine a circuit as a complete, unbroken path. Okay? If the electric circuit, if there's a break anywhere on that electric circuit, the electric current comes to a stop. Just like if you have a NASCAR race. If there's something happens on one part of the track, well, all the cars stop. Everything comes to a halt. There are some materials that allows electricity to flow through them very well. Okay? Metals are just an awesome example of this type of material. Okay? Electric currents flow through metal extremely well. Water would be another example of this. Again, the formal definition, a material through which a charge can flow easily. If you said conductor, you are correct. Good job. There are materials that allow electricity to run through them very easily, almost with very little to no resistance. Then there are materials that electricity just cannot seem to flow. Okay, you can have an exposed wire, and you touch it with metal, well, you're going to shock yourself. But if you touch it with wood or rubber or some other type of this material, well, the electricity, the current just can't travel through it. The formal definition, a material through which charges cannot flow easily or not flow at all. There's a reason we coat wiring with rubber or plastic. Okay, that rubber or plastic is an insulator, a material that the current inside the wire can't come out. Okay, if you're ever around electricity, especially in a dangerous situation, and I hope that never happens, but if you are, an insulator like rubber will be your best friend because it can help protect you from that electric current. Okay, this is tricky for some students. A lot of people think that electricity just moves with no force or nothing pushing it along. It just moves on its own. But unfortunately, in nature, and we talked about this a lot this year, things just don't move. Air, the wind, moving air, doesn't just move on its own from one place to another in the sky. It goes from areas of high pressure to low pressure. A roller coaster comes down because it has high potential energy when it's up, and then that potential energy is converted to kinetic energy as it goes down. Well, electricity is the same. Electricity goes from one place to the next, but it must have a motivating force, and that motivating force is the difference in potential energy. So the formal definition is the difference in electrical potential energy between two places. If there is a difference, especially if you have a high electrical potential energy in one place and a low electrical potential energy in another place, well, the electricity is going to want to move from high to low. Just like a roller coaster moves on its own from a high point to a low point. Good luck with this one. If you said voltage, you are correct. Again, before we take this test, spend a little time reading the book about voltage, reviewing this one. It's a tricky one. Okay, now is a great time to take a break. We have been doing this for almost 15 minutes. It's probably not smart to continue on for another 15 minutes without taking a short break. So recharge, drink some water, get some food, and then when you're ready, click on Coach Seckinger and Electricity Part 2, and we'll continue. See you in a few minutes.